Well, this is part 2 of our review for the test on short and simple lectures on 1D motion on the kinematic equations, and we're now going to switch over to the other view. For this problem, we have a car that goes 40 meters in 5 seconds. What are the values of all the things that can be determined from these two values? From the information given in the problem, I've pulled out our little check sheet and wrote in the first two, which is we went 40 meters in 5 seconds. So now comes the question, what else can we know? Well, since we weren't given anything else, I think we're probably safe in assuming that the initial time was 0, the initial distance was 0, therefore the final distance was 40 meters. The final time was also 5.0 seconds. As far as that goes, now we need to find out average velocity, change in distance over time. Okay, I got 40 meters. I got 5 seconds. Last time I checked, 40 divided by 5 was 8 meters per second is the average. Now we also know that the average is final plus initial. Velocity initial should have been 0, so the final would have been rearranged to be 2 times the velocity average minus velocity initial, which gives us, it was 16 meters per second, if we are assuming we had uniform acceleration the entire time. If we didn't have uniform acceleration, if it was a constant velocity, then this would apply, but for our purposes here, we're going to assume that it just went 8 meters per second. If it started at 0, then we say 16. The change in velocity is 16 meters per second. Change acceleration is delta v over delta t. We got 16 meters per second times 1 over 5 seconds, which will give us 16 divided by 5, which is 3.2. For our third example, we have a motorized racing remote controlled car, RC. Starts at rest, reaches a speed of 88 miles an hour in 20 seconds when it crosses the finish line. What is the total distance from the starting line to the finish line, and anything else you can determine the SI units? Well, taking that information and pulling out our check sheet, or checklist sheet, I filled in that we had a change in time of 20 seconds. Final velocity was 88 miles an hour because it says it reached a speed of 88 miles an hour in the 20 seconds when it crossed the finish line. And I think we're safe in assuming that the finish line was 0.0 and the stopwatch started at 0 there, and then it wasn't going anywhere before it started. However, we have a problem with our units. So at this point, we need to now change 88 miles an hour into meters per second. We have 88 miles per hour. Well, we know there's 1.6 kilometers in 1 mile, so that takes care of that part. And we also know that there are 3,600 seconds in 1 hour. So, oops, I have that backwards. So now I have to X that out and go 88 miles an hour, 1.6 kilometers for every 1 mile. And I want, for every 1 hour, I have 3,600 seconds. Pull out the calculator and see what we can do, because I can get rid of miles this way, hours that way, and that's going to give me kilometers per second, and then we're going to need to change that into, there's actually, I can just write 1,600 meters and save myself a step. So 88 times the 1,600 meters per kilometer gives me that number, divided by the 3,600 seconds per hour, and we are doing 39.11, continuing, meters per second as our final velocity. So plug that back in. velocity final becomes 3911 repeating meters per second. Now, can we figure out average velocity? Of course we can. We're very bright. We can also figure out the delta. The delta was actually given to us for free here because we had no zero. We get a zero. Average. Take what you have, 3911 plus 0, divide by 2, and that gives me 19.55 repeating meters per second. I don't know if we need that yet, but we could probably figure out the distance. As far as that goes, distance is velocity, or is distance times time, therefore distance becomes velocity average times multiplied by time. So times 20, and we have one calculation that says 391.11 meters. So change in distance, 391.11 repeating meters. Distance final, well, since we started at 0, 391.11 repeating meters. Time final, well, we already had that, 20 seconds. Now we just need to figure out what the acceleration is. Well, change in velocity, 39.11, divided by the 20 seconds. That gives me an average acceleration of 1.955 meters per second squared. Now gravity is 9.8, so when you trip and fall, you accelerate much faster than this little car did. Now for part 3, more complicated problems because time and distance are not given. Honors students in physical science and all you physics types, you might want to pay attention to these. They're probably going to be on your test. As far as that goes, of course, that shouldn't be that much of a surprise to you. So for example, problem 4, we are given that a rocket accelerates at an average of 50 meters per second from its launch pad and reached an altitude of 15,000 kilometers before the engines ran out of fuel. What can you determine about its velocity and how long the fuel lasted? Well, taking the information given on the problem and putting it on our fill-in-the-blank sheet of what do we know, what do we don't know, we have a change in distance, 15,000 kilometers, or 1.5 times 10 to the 7th meters, or 15 million meters. So it'd be 15 megameters. Our acceleration is 50 meters per second squared. Hopefully you can see that. And we start as a rocket on a rocket launcher. We've seen rockets go up before. They don't, time would start off at 0. The distance above the pad is 0. Distance final, therefore, is 15 megameters, or times 10 to the 7th meters. Velocity initial, wasn't going anywhere before it was going anywhere, so we're pretty good there. But now, we don't have any times, so that forces us to have to use this guy here. Now, let's take a look at it. How fast was it going? 0 meters squared plus 2 times the acceleration, 50 meters per second, times the distance of 1.5 times 10 to the 7th meters is going to give us velocity final squared. And if you look at this, I'm going to have meters squared over seconds squared. And now we just pull out the calculator. 2 times 50 times 1.5 second times 10 to the 7th meters. And I get that. Let's put that in scientific notation because our numbers are gotten it. 1.5 times 10 to the 9th. 1.5 times 10 to the 9th meters squared seconds squared. Therefore, take the square root and we can go raise it to the 0.5, which is, and that gives me 3.873 times 10 to the 4th meters per second or if you like that in floating notation, 38,729, so 0.83, so 38,730, approximately 38,730 meters per second was the final velocity it was going before it ran out of gas. Hopefully too much of that was not on the bottom there. Once again, I just punched through the numbers. Took the square root of this, got me that. Did a little rounding off so we can talk about it in conversation, because this does get to be a bit much. Now, I have the final velocity, 38,730 meters per second. What is my average? Well, I add these together, divide by 2. So divide by 2, and I should get what? 19,365. Double check that. Yeah. Meters per second was the average velocity. Let's double check that we're actually on the right track. So we have, that's the average velocity. We don't know the time yet, do we? But I bet I could take this, and this becomes t equals velocity, distance over velocity. So I got, or the average velocity, so I got 15,000 kilometers, or actually I need meters per second, 1.5 times 10 to the 7th meters divided by 19365 gives me 774.6. 774.6 seconds. Sticking to our 4 digits here. So delta t was 774.6 seconds. Now we can also double check this by solving this for d to make sure it was good. We can also double check this for velocity final. We have a velocity final of 38.6. Let's go here. Initial was 0, so we have 50 times 774.6, and I get 38,730, 38,730, 38,730 meters per second. And so far everything checks out. Time final would be 774.6 seconds. If you wanted to, we could also solve this for d and move it around as far as all that goes. So what do you do when you want to do that? Velocity final equals velocity initial squared plus 2ad. This becomes velocity final minus velocity initial squared is equal to 2ad. I want to know what d is, so I divide that. Velocity final squared, velocity initial squared, 2a equals d. My final velocity was 38,730. 38,730 squared minus 0 squared divided by 2 times 50. 38,730 squared divided by 100, and I come out 15, once again 15 million, or 1.5 times 10 to the 7th meters. This is because we did round off this a little bit on our approximations. So we've double checked our answers, and that's about as nasty as the problems can get. Hopefully that answers questions for you. If you have any other questions before the test, please see me. Well, to try to wrap this all up, let's start at the things. You have an upcoming test. You should, or are expected, so you should know and are expected for the test to know nature of science questions, which is the fundamental assumption of science concerning the rules. That assumption is that there is one set of laws for the entire universe. Doesn't mean we know what they are, but we have to assume there is one set of laws for the entire universe, and we also know that most things in science can be described mathematically, and that I can use numbers to tell me the answer to questions like how much and how far and that kind of stuff, which is why we use math all the time. You also need to be able to say the correct order of the scientific method using preach as the starting point. You have your purpose, your research, your experiment, the analysis of data, the conclusion, and it's all about the hypothesis. And of course, when you do it, and you wrote it like for your lab report, you wrote your purpose first, your research, then the hypothesis, the experiment, which is your do it part, that all the math happens in the analysis of data, and all that's where all the data goes. And in the conclusion, you need to be able to tell me, was your hypothesis right or was it wrong, and why it was right or wrong. That's why you need to write a hypothesis that can be answered in a binary form of correct or not correct. I predicted the gravity here at my classroom will be within 5% of the expected value on planet Earth. I can check the math and know, am I within 5% or not? Where if I say it's going to be Earth-like, well, that doesn't tell me much. Or it's exactly like it. Well, if you say exact or the same as, you gave yourself zero wiggle room at all for anything. So you have to be sure to be careful on that. The metric system, you need to know meters, kilograms, and seconds are the first three basic units. There are 7 right now. You've only been exposed to 3 of them. You'll be able to convert from inches to centimeters, where there's 2.54 centimeters in 1 inch. 2.2 pounds in 1 kilogram, and be able to do problems of that nature. I expect that you can create the what do you know, what do you need to know list when we do these kinematic equations, and I expect that you can produce the basic kinematic equations and translate them, that the average speed or velocity is change in distance over change in time. Your average velocity is also velocity 1 plus velocity 2 plus velocity 3, so on and so forth, divided by how many things you had. Usually we just have 2, so your velocity average is final plus initial divided by 2, and you might be able to move that formula around in case I give you an initial and an average and say find me the final. Or maybe I'll give you a final and an average and say find the initial. You also need to know that the velocity final, where you end, it's going to be where you start plus your acceleration multiplied by time. Your final position on distance is going to be equal to distance initial, where you start, plus how fast you were going multiplied by the time you were going that way, plus the change caused by acceleration times squared multiplied by 1/2. That's what this formula is. So if I say you need to say this in words, you need to be able to do it. I might give you in words, say tell me the formula, or I might say here's a formula, tell me the words. And then we have the time-independent equation, which is your final velocity squared. So it's not the final velocity, it's the square. It's where it's squared, is equal to what you started at squared plus 2 times the acceleration during that time, during the trip, multiplied by the distance to trip by. Average acceleration is delta v over delta t. And you'd be able to go backwards and forward and move those letters around. Otherwise, you're going to have a bit of a problem. But there should be absolutely nothing on the upcoming exam, test, whatever you want to call it, that is a surprise. You should see this coming. Once again, you're going to be able to use your book covers provided you put a proper book cover on. So you need to go on the internet and figure out how to wrap a book up like you do a Christmas present, except the book has to be able to open and close. And also, I'll be checking the books. Have you written your name inside the cover? If you do not have the correct numbered book and with the cover on it, or at least your name on it, you're going to have points off, because that's going to be a test question. Can you show me your book with your name written in there, name and class period? And then if you have it covered, you can use the notes. If you don't have it covered, you have nothing except whatever's in your brain. Good luck. talking to you about questions.